Okay, let me start today's class. So, as you can see in the blackboard, you already have something written. Probably you have been able to figure out what it is. So, yesterday I was considering this equation number A, okay? And I was trying to solve it using an infinite series of this form, By substituting this infinite series in this equation A, I was trying to find out the solution, and eventually, I ended up in this expression. Is it okay? Fine.
Yes, sir.
Okay, because today I'm not sharing my desktop, I'm sharing my camera. So it's kind of a new experiment. So I want to have a better resolution of the video. So let me see whether these experiments turns out to be successful or not. Okay, fine. So now, if you look at the final equation here, so what it is going to do to us, like if I use this portion by equating the coefficients of different powers of x to 0, what I am going to get. So this is going to lead me to the recurrence formula, A2 that is equal to minus half p into p plus 1 a naught, right? Similarly, this one, what it is going to do, okay. Say, okay, let me write it down first and after that. Okay, so A3, so this is going to be equal to 1 by 6, and you'll see that these are all A1s. So once I transpose these to the right hand side, this is going to be 2. And then this is going to be minus, or maybe what I can do, maybe I can still do something like this, minus 1 by 6 p into p plus 1, and then let this remain as minus 2. This is A1, right? And if I look at this expression, then you will see that this is nothing but p squared plus p minus 2. So I can decompose this p as 2p minus p. Is it okay? If I decompose this p as 2p minus p, so then this is going to give me 1 by 6, then your p minus 1. Is it? Am I fine? Just a minute. Not p. Just a minute. So this is going to give me p into p plus 2 minus 1 into p plus 2, right? So basically, yeah, I'm fine. P plus 2 A1. Is it okay with everybody? Fine. So this is going to give me this, and then let me check this equation now. Okay, and this equation, it is going to be valid for n greater than equal to 2. Okay. So from here, what I'm going to get, as before, what I can do here, your a n plus 2. So this is 1 by n plus 2 into n plus 1. So maybe as we did here, what I can do, I can simply rope in this negative sign there, so that I can make like this p into p plus 1, come in front, and then from this I am going to get minus n squared plus n, and this is a n. Fine? Is it okay? Fine. So what this is going to give you, you will see that. So this is going to be p squared plus p, and then if I do it like say p squared minus n squared, and then your p plus n. So this is going to give me p plus n, p minus n, right? And this is going to be p plus n. Am I okay? And squared plus n. Yeah, I should be fine. So eventually it is going to give me your p plus n into p minus n plus 1. Am I okay? Or did I make some mistake somewhere?
Sir, minus 2n should be there, no?
Minus n.
Minus n, yes, sir.
Just a minute. This is minus n squared plus n. Oh, there is another minus. There is minus 2n. So basically, with this 2n, this is going to be minus n, right? This is going to be minus n. So this is going to be p minus n. Okay. So eventually, I am going to get p minus n common, and then p plus n plus 1. Okay. Thank you. So I am going to get this as p minus n, p plus n plus 1. Okay. So I'll simply substitute here. So this is equal to minus 1 by n plus 2, n plus 1, and then p minus n, p plus n plus 1 into a n. Okay, fine. So this is my recurrence formula. This is my recurrence formula. So I have everything now. I have everything. So basically, and again, you have to write that this one is valid for all n greater than equal to 2. Okay, this one is valid for all greater than equal to 2. I mean, just simply don't write some kind of recurrence formula without giving the ranks for n. Okay, fine. So now, if I use these two recurrence formula, and if I start from n equal to 2 here, that is going to lead me to your a4. That is going to be equal to minus 1 by. Maybe I should start with. It will be easier for us to. Okay, fine. So 3 into 4, and then this is going to be p minus 2, and then p plus 3, right? And this is a2, right? And again, if you substitute the expression for a2 here, that is going to give you. Actually, this is going to be plus. So I am going to get 2 into 3 into 4, then p into p minus 2, p plus 1, p plus 3. This is a naught. Okay, and then if I plug in n equal to 3, this is a5. A5 is going to be minus 1 by. This is going to be 4 into 5, and then p minus 3, p plus 4. This is a3, and if you plug in the value of a3 here, this is going to give you 1 by what? 6 is nothing but I can decompose into 2 into 3 into 4 into 5. Then this is p minus 1, p minus 3, then p plus 2, p plus 4, and this is a1. Okay, so basically a pattern is coming out, right? Basically a pattern is coming out. So using all these, and similarly I'll be able to get a6, a7, etc. So using all these coefficients, what I'm going to get, like if you recall, my series was like y equal to a n x to the power n going from 0 to infinity. Okay, and this is for the first time I am doing it. Later on I am going to substitute everything, curtailing some mistakes. So say this is a1x, a2x squared, a3x cubed, and so on. So what I can do, because see what is happening here. Now you are getting all the even terms, as a what? Function of a naught, isn't it? As a function of a naught or
Yes.
some multiple of a naught, right? And similarly, the odd ones, you are getting it as a multiple of a1. So that is why I am going to separate it into like in terms of a naught ones and in terms of your a1 ones. Is it okay? So then what is going to happen? This is going to give you like a naught 1, and what is a2? A2 was minus half p into p plus 1. So a2 corresponds to x squared. Then comes a4, that is plus your just a minute. I missed one. 2 is there. Okay, fine. 2 into 3 into 4, then p into p minus 2, p plus 1, p plus 3, your x to the power 4. So next term, it is going to be a minus. It is going to be 2 into 3 into 4 into what? 5 into 6, right? 5 into 6, and if I follow this pattern, this would be p minus 2, p minus 4, then this is p plus 1, p plus 3, p plus 5, your x to the power 6, and then plus. You may be thinking why I am writing so many expressions here. So there is a purpose behind it. Later on you are going to see. And similarly, what I can do now, I can substitute all the odd powers. So this is going to give me a1. Of course, the a1 was the coefficient of x. Then will come a3 with x to the power 3, and then a5 and so on. So now a3 was your minus, I can write it 2 into 3, p minus 1, p plus 2, this is going to be x cubed. Maybe, sorry, this is not equal to, let me write it down a bit, sorry about that, x minus, so 2 into 3, then p minus 1, p plus 2, your x cubed, then plus 2 into 3 into 4 into 5, and then p minus 1, p minus 3, p plus 2, this should be p plus 4 x to the power 5, and then your next term should be minus into 3 into 4 into 5 into 6 into 7. Just I'll just p minus 1, p minus 3, p minus 5, and then here p plus 2, p plus 4, p plus 6, and this will be x plus 7 plus and so on. Okay, fine. Okay. So now, what is happening here? See, beforehand, I had assumed that p is non-negative, right? P is non-negative. Okay. So I'll come back to p again, but before that, I want you to have a closer look. I want you to have a closer look at the two series here. The two series here, like one where in one series a0 is the constant and the other series a1 is the constant. So basically, I am getting something like a0 y1x, right? And then a1 y2x. I am getting something like this. Okay, where y1x is given by this and y2x is given by this within the parentheses, whatever is there. Okay, so now if you look at these y1x and y2x, I mean they are not like the elementary functions or combination of elementary functions that you found earlier. Okay, so that should give you an idea that if we use power series expansion as our solutions, it may not necessarily land you into some elementary function or combination of elementary functions. Is it okay? Fine. We may not be that lucky. That is my point. We may not be that lucky. Okay, fine. So now let us try to find out the radius of convergence. See, I have got a solution like this, right? I have got a solution like this, and here you have seen that the solution can be broken into something like that, where I have got two individual power series again, right? In terms of y1 and y2. Right? Is it okay with everybody? Fine?
Yes, sir.
Yes, sir.
And both the power series for y1 and y2, they were taken about x not equal to 0. Right? They were series about your x not equal to 0. Like say if I consider a power series like this, x minus x not to the power n, right? Okay, so here for both the two series, I have x not equal to 0. So that means I have found two power series about x equal to 0. Is it okay? Fine. Because I would try to bring about some conclusion from what I am going to do now. Okay, fine. So now let me try to find out the radius of convergence, and of course we are going to find out the radius of convergence about x equal to 0. Okay, so if I look at the individual terms of power series y1x and y2x, then you can see that for the say first series. For the first series, your say suppose I denote the nth by say an, nth term by an. Okay, so then an is going to be like say if I start from n equal to 0, obviously this is going to give me say minus 1 to the power n, and then if I consider these to be say corresponding to n equal to 2 say, right? So this one, or say these to be corresponding to n equal to 3. So obviously this is factorial 2n. Is it okay with everybody? Fine. And then I have p into p minus 2, and what is happening? It is finishing at p minus 4, whereas this was 6. 6 is 2 into 3 here. So 2n plus 2. Is it okay? And then here it is p plus 1, p plus 2, and up to one term, p plus 5 say. So if t is stopping at p plus 2n minus 1, is it okay with everybody? Fine?
Yes, sir.
Fine? Okay. So, and then this is x to the 2n, and n going from 1 to etc. Is it okay? Fine? Okay. So similarly, for the second series, let me see what comes out. And again, see, like probably for many of you, you may be finding this power series solution kind of things kind of boring. But you have to get rid of that thought that, oh my God, it is so boring. No. I mean, you try to find some interest in it, and then you will see that it is really, really interesting. Okay, I'll tell you why. So now, let me try to find out for the second series. Suppose for the second series, and again, see, let me tell you, this indexing, it is up to you how you are going to take it. You may start from n equal to 1. So you have to adjust accordingly. Okay. So here in the second series, I figured out that if I start from this as n equal to 1, my life becomes much simpler. Okay. So let us try to do that. For the second series, my an. So obviously, what is going to happen? The first term is This is this is positive, and this is negative. So what I'm going to write here? Minus 1 to the power. I think I can write it as simply n. Okay, and this is factorial 3. This is factorial 3. If I consider this to be the second term, this is going to be, or say if I consider this to be the third term, so I can write it as 2n minus 1. Okay, fine, and then it is simply going to be p minus 1, p minus 3 up to, if you look at this, if you consider this to be the fourth term, then what is going to happen? P minus 5 P minus 5 can be written as what? P
minus n plus 1.
P minus n minus 1, basically. Eventually, I'll check it. I'll check it. 3 is just a minute. Here. Here 3 is 2n minus 1. Did I miss just a minute? 23 into 4 into 5. This is 7. So 3, if you connect it with 2, that is this 2n minus 1. If you connect it with 1, 2, 3. Just 2, 3. Did I miss something? One term. Did I miss one term somewhere here? No, I'm fine, right? No, that has to be, that cannot be 2n. That has to be in terms of something like 2n minus 1 or something like that. It cannot be that. Did I miss
minus
something?
2n plus.
Minus 2n plus 1.
That will be.
Yeah, minus 2n
3.
plus 1. But then did I miss some term here?
So 2n minus 3 will work.
No, 2n minus 3. No, then maybe I have to change the indexing here. I may have to change the indexing here. So it is, if I call it, say, second term, if I call it second term, so should I start with 0 here as well? 0, 1, 2, 3. So then this is going to be my 2n plus 1. This is going to be, so should I start with 0, 1, 2, 3 here as well? I think that is going to be easier for me then, right? So then what is going to happen? Yeah, then this is going to be 2n plus 1. Okay, this is going to be 2n plus 1. And then, yeah, so then 3 is again going to be 2n plus 1. So this 5 is also going to be 2n, right? So basically, it is 2n minus 1. Okay, and then this part is going to be, yeah, it is up to 2n. So 3 plus 2, 3 plus 4, up to 3 plus 2n, and then x 2n plus 1, and here again your n is going to go from 0, 1, 2, 3. Yeah, I think
So that should be p minus 2n plus 1.
Which one? This one?
P, yes.
Sir, you can put a bar or a bracket.
Yes.
No. See, now
minus
0, 1, 2. Oh, okay. 2n minus 1. Yeah, fine. Thank you. Yeah, absolutely. Yeah, you are fine. Yeah. Okay. Because now this is 0, 1, 2. Yeah, fine. Okay. So I have figured out, what these terms are. I still don't want to erase series because I would like to draw your attention to something else later on. Okay, anyway, so let me just concentrate in one series. And the other series you can easily work that out. So now, see, as I have told you, if I want to find out the radius of convergence, then simply I could have done something like your an plus 1 as limit n tends to infinity, right? That would have given me the radius of convergence. Fine, we have already done that in yesterday's class. But here, instead of doing this, I would still like to stick to the original ratio test. Okay, I'll tell you why. For this particular example, I want to do that. Okay, so that is, now let me try to do let me try to do like this one. Limit n tends to infinity, your an plus 1 divided by an, say for 41st series. Okay. So now what is going to happen? So this is limit n tends to infinity, n tends to infinity. I'm running out of space here. Okay. So now what is going to happen? Like say an plus 1, then here you are going to have one extra term, right? So that extra term p plus 2n plus 1, isn't it? Fine. What I'm saying is that once I plug in the values of an plus 1 and an, after cancellation, what you are going to have? You are, see, this is up to this, just a minute. Up to this, all the terms are going to be there, right? So now if you plug in, instead of n, if you plug in n plus 1, so it is going to be minus 2n minus 2, this is going to go out. So that extra term is going to be what? P minus 2n simply. Is it okay? Fine. From this part, okay? And from this part, what we are going to have? We are going to have P plus 2n plus 1. P plus 2n plus 1. Okay? And then here I am going to have, say, 2n plus factorial 2n plus 2, right? If you divide it by factorial 2n, then you are going to be left with 2n plus 2, 2n plus 1. Is it okay?
Yes, sir.
Are these letters visible?
Yes.
Yes, sir.
They are visible?
Yes, sir.
Okay, fine. So, and then what is going to happen? Here? That is only for that one. I am doing this stuff. Here you are going to have an x squared. Generally, we expect x, right? Earlier when we defined, the radius of convergence for an infinite series, then somehow we got mod of x, isn't it? This I have done from the definition in order to show you that it is not necessary that you are always going to end up with only mod of x. Here, eventually, see, this is going to give you mod of x squared, isn't it? Right? So now, if you work it out, what you are going to get, divide everything by. So from here, you are going to get then here again 2 plus 1 by n, right? And mod of x squared. I'm sorry for this clumsiness, but please bear with me for the time being. Okay, so eventually, see here, I am going to have, because this is absolute value, 2, 2, and again 2, 2. So this is going to give you 1. Is it okay? Is it okay with everybody?
Yes, sir.
Right?
Yes, sir.
Right? And you know that, this is going to converge if this is, mod of x squared is less than 1, or basically if mod of x is strictly less than 1. Is it okay? And see, I could have got the radius of convergence from this formula also. But see, this is to show that, this is to show that you don't always end up with mod of x. Okay, even then it is going to work. Even then it is going to work because here the successive terms are coming at a difference of that exponent 2. Okay, so I have found out that the radius of convergence is 1 here. Is it okay with everybody? Even you can use this formula also. Even you can use this formula also. Okay, only there you have to claim that this happens, and only after that you get this. Okay, fine. So similarly for the second series also, you are going to end up with radius of convergence as 1. Okay, fine. So now this is fine. I have got the radius of convergence as 1. Do you find something interesting about this 1? Like, can you relate this 1 to something here? Can you relate this radius of convergence, which I have found as 1 for this particular series, or both the series? Can you relate this to something? Yes? Oh, I have already. Okay, anyway. Can you relate this to something?
Sir, please repeat this question. Question is not clear.
Say, I have found out that the radius of convergence is 1. Okay. Can you relate it to something? Something like, say, for this equation, for this particular equation. What was 1? Can you remember it from yesterday's class?
Plus and minus
Singular
one
point.
Yes. What was 1?
Singular
Singular
point.
point. Yes. We have figured out that x equal to plus minus 1, they will be singular points, right? Okay. Now I have found out that for this interval, right? For this interval, the series converges. Okay. And again, here the series was about x not equal to 0. Okay. So does it give you about some idea about the length of the radius? I mean,
It
yes.
is the distance to the nearest singular point.
Okay, this is the nearest one.
Singular point.
Exactly. So the radius of convergence is always going to be from the center of the power series, or from the center of the power series to its nearest singular point. Is it okay? Fine.
Yes,
Is it
sir.
okay?
Yes,
Are you
sir.
getting my point? Are you getting my point? See, here I was considering it both the power series about x equal to 0, and I have found out that at the very beginning I have found out that here what was there, px equal to minus 2x 1 minus x squared, and qx was p into p plus 1 minus x squared, right? So we had seen that x equal to plus minus 1 were the singular points, right? Okay, so because we cannot get we cannot have px and qx to be analytic about that singular point, so that is why we were seeking a power series solution somewhere else other than those singular points. Is it okay? Right? And here we sought a power series solution about x equal to 0, which was not a singular point, ordinary point, right? Okay, so now again we have found out that this radius of convergence r, it is nothing but distance of the center of the power series from the nearest singular point. Okay, so you may found more than one singular point. Here they were equidistant. Say, suppose there may be a function like you may have some two factors like say x minus 2, x minus 3, something like that. So then you will find out that your radius of convergence is going to be 2 in those particular cases. Are you getting my point? Right?
Yes, sir.
Yes, sir.
Right? Because in those cases, say, suppose this was 1, say this was 2, this was 3, right? So in those cases, what is going to happen? So 2 is going to be nearest to the center. Okay, fine. I didn't want to, erase those solutions out, but I have erased it. I'll have to again write it down. But anyway, I think I'll just explain it. Okay, fine. If you recall, the solution was something like. I exactly don't remember. I think it is P. Was it P plus 2 or? First one was P plus 1 or P plus 2? I think P plus 2.
P minus 2.
No, because I remember.
P plus 1, sir. P plus 1.
P plus 1.
Yes.
Yeah. Okay. So P plus 1 and this was factorial 2, right? X
Yes.
squared. So this is P plus 1, P plus 3, P plus 3, factorial 4, I think, right?
Yes, sir.
Factorial 4, X to the power 4. Okay, fine. It was like this, okay. Then the second series was, and this was what?
P minus 1, P plus 2.
Okay. P minus 1, P
P plus 2. P plus 2.
plus. Okay. I'll recall. Minus. Okay. Okay, fine. See, now here I have already told you that P is non-negative. P is non-negative. P is non-negative. Okay. So that leaves us with the option that P can be, either a fraction, right, or an integer. Okay, fine. So if P is a fraction, so definitely in that case, all these coefficients, they will be non-vanishing. Are you getting my point?
Yes, sir.
Yes, sir.
Right? But if P is an integer, so then what is going to happen? Say suppose P is equal to 0. Then definitely what is going to happen? If P equal to 0, the first series, it is going to terminate here itself, isn't it? Because P equal to 0, it is going to annihilate all the successive terms. Is it okay? Fine. So from the first series, I'll be left with only A naught. Is it okay with everybody?
Yes.
Yes, sir.
Right? Whereas the second series will continue. Is it okay? Fine. Similarly, if P is equal to 1, the second series is going to vanish from here onwards. Okay, fine. And again, P equal to 2, the first series is going to vanish from these terms onwards, and so on. Is it clear to everybody what I'm trying to explain when P is an integer? So what I want to tell you is that when P is an integer, one of the series, it is going to terminate at some juncture, whereas the other series is going to remain infinite. It is going to continue. Okay, so basically what happens? One series, it becomes a polynomial, simply it reduces to a polynomial, and the other series it continues. Is it okay? Fine.
Yes, sir.
Yes.
Fine?
Sir.
Yeah. So that is why I didn't want to erase the blackboard at the time. Okay. So fine. And yeah, now the easiest of all the questions, because you must have seen at home now. So what is this equation we are considering? What is this equation called?
Bessel's.
Legendre equation.
Legendre's equation. Okay. Okay. Fine. So Legendre's equation. So now you have found out that like say, if you plug in integer values of p here, okay, in one of the series, you are going to get a polynomial. Okay, fine. So if you simply extract those polynomials out of only one of them, whichever has been curtailed, whichever series has been curtailed, so those polynomials, you know what it is, Legendre's polynomial. Is it okay now? Fine. Those are called Legendre's polynomial. Okay. So now I would like to do one theorem. I would like to do one theorem. Okay. So the theorem statement is very big, but don't need to worry about it. I'll just explain it, and you will see that proof is very interesting.
Sir, you found out the radius of convergence of one series. So next
Yeah.
you have to find out the radius of convergence of the another series also.
Yeah. So
Then we
that will also come out to be one. That I'm leaving it as a homework.
Okay.
Okay. Both of them, they are going to come as one. Okay. So I'm going to call it as theorem A. Theorem A. Okay. So here, let x not be. Just a minute. Maybe I should erase the board a bit. Okay, so till the blackboard dries up, let me tell you another thing. Like say, whatever power series we have done, whatever power series till now we have done, the recurrence formula that you have seen, that in the recurrence formula, it was two-term, recurrence formula. Like say, what was happening? You were expressing one term in terms of another one. Like say an plus 2 in terms of an. Is it okay with everybody?
Yes, sir.
Right? And in yesterday I was considering a first order differential equation. It was like say something like an plus 1 in terms of an, right? And they can be easily worked out. They can be easily worked out, straightforward. But it is not necessary that you are always going to get only a two-term recurrence formula. You may get more than two terms recurrence formula. So then your one term will be expressed in terms of another more than one. Like say you may have some expression involving an plus 2, n plus 1, and n. So then you will have to express n plus 2 in terms of n plus 1 as well as n. right? So your life may not be that easy. Okay, you have to find some other way out. Okay, so if time permits, I'll take one example for that. Okay, so theorem. Okay, so let x naught be an ordinary point of the back, you know what that is. This is equal to 0. Okay, and your a naught and a1 be your arbitrary constants. They be arbitrary constants. Okay, so then what this theorem say that then there exists a unique function yx, there exists a unique function yx that is basically that is which is analytic at x naught, and again it is not only analytic at x naught, it is a solution of the above equation. Let me call it a solution of a. Okay, of course that is solution of a in a certain neighborhood of x naught. Certain neighborhood of x naught. Okay, and not only that, it also satisfies the initial conditions. This is y at x naught equal to a naught and y prime and x naught equal to b naught. A1, of course, see this choice of a naught and a1, that is going to depend upon the choice of our infinite space. Okay, fine. And next part is very, very important. Furthermore, if the power series expansions of px and qx are valid in the interval mod of x minus x naught strictly less than r, and of course r is strictly greater than 0. Then what happens? Then the power series expansion of the solution is also valid in that interval, or you can say that it also converges for the same radius of convergence in that interval. Is it okay? So it is same interval. Okay, fine. So basically, firstly, what we will have to do, we'll have to show that if you choose a power series solution, so that power series solution is, going to be. So basically, like, firstly, you simply look at Px and Qx. The very first condition that has been given that, like say x0 is an ordinary point for this given differential equation. And what is the meaning of that? The meaning of that is Px and Qx, they can be expanded as a power series. That means convergent power series about x equal to x0. And I have already been given that they are valid in this interval, given by this interval. So now I have to prove that I can always find a unique solution. And that solution is going to be an infinite series about the ordinary point x0. And that solution is going to be unique. Okay? And it is going to have the same radius of convergence as the power series expansions of Px and Qx. Is it okay? Fine. Now, have you understood the statement of the theorem? What it is telling you? Is it okay? Then I will proceed to proof.
Yes, sir.
Fine. Okay. So I think I'll be able to prove only the first one. The radius of convergence probably I'll have to leave till tomorrow. But another thing I want to emphasize is that, see, the validity or the validation of the theorem, we have already done previous example. So when we had taken the Legendre's equation. So if you recall, what was happening? Like the Px and Qx. Let me just explain that. So I guess I can erase this. So I prove. I will recall the theorem for this proof. So in fact, we have already validated this. Okay. So let me tell you how we have validated it, and then I'll proceed to the proof. Okay. Then I will proceed to the proof. Okay, so if you recall, in Legendre's equation, Px was like minus 2x, and okay, so now both Px and Qx, they were analyzed equal to 0, right? Is it okay? Fine. Now, simply look at this. What is going to happen? So your Px, this I can write as c minus 2x. So if you go for the expansion of 1 minus x squared to the power minus 1, right? So then I am going to have something like this, isn't it? Is it okay with everybody? Yes?
Yes, sir.
Fine. So I mean, likewise for this series. Fine. So now you can easily see that both this series and the series I would have got from here, they will have this as their interval of convergence. Is it okay? Fine.
Yes.
Yes, sir.
Isn't it?
Yes.
Fine. And we had already found out that the solution that we obtained in something like a0 y1x plus a1 y2x, right? That solution also had convergence 1. So in fact, we have already validated this theorem. Okay. So now let me give you a proof of that. So here, some of the things that we learned earlier is going to come in handy. Okay, fine. So proof. Here, what we can do, I mean, without loss of generality, we can assume that x not equal to 0, right? Because if it is non-zero, I can always use some kind of shifting, right? And I can do the proof, and then eventually through the same shifting transformation, I can retain my original series. Is it okay? Fine. So now, since your Px and Qx are analytic about, say, x not equal to 0, therefore Px can be expressed as this, say, Pn x to the power n, and Qx can be 0 to infinity. Fine? Okay? So now, and again, by the given condition, both these series, they converges in this interval. They converges in this interval for some r greater than 0. Okay. So now let us assume that your yx, let us assume that your yx equal to this a n x to the power n and equal to 0 to infinity. This is a power 6 solution. Okay. So then what is going to happen? If I plug in this in my given equation, it must satisfy it. Okay. So now my given equation is your y double prime plus pxy prime plus qxy. This is equal to 0. So I'll straightforwardly plug that in. So then if I plug that in here, that is going to give me, now you are experienced enough, I am to ask you, I am straightforwardly going to write it and see what is Px? Px is Pn x to the power n, n goes from 0 to infinity, right? And your y prime, this is n equal to 1, to infinity. So n a n x to the power n minus 1, and then your qx is n equal to 0 to infinity this, and then n equal to 0 to infinity your a n x to the power n. So this is equal to 0. Right? So far so good. Okay. So now here the first thing I have to see is okay, let it be like this. Let it be like this. Don't forget about it. And what is going to happen here? Eventually, you will see that all the power series, like say this one, and this one, all are going to start from x to the power 0. X to the power 0. So I don't have to do any adjustment here. Is it okay? Or not? Is it okay or not?
Yes, sir.
Right? Everything is going to start with this. Okay. So that is why what I am going to do in your next line, please write implies. So I am going to make all the powers of x as x to the power n. So basically what I am going to do, I am going to change this. So if I plug in n minus 2 equal to p, so n is going to be equal to p plus 2. And when n equal to 2, p is going to be equal to 0, right? So You know the trick. So that is why what I am going to do, I am simply going to start this from n equal to 0, and then this is going to be replaced by n plus 2, n plus 1, then a n plus 2 x to the power n, right? And similarly, this one, if you start from n equal to 0 by plugging in n minus p equal to, sorry, n minus 1 equal to p, right? You know the tricks now. So this is going to be starting from n equal to 0, and this is going to be n plus 1, a n plus 1 x to the power n. Is it okay with everybody?
Yes, sir.
Yes? Yes? So, like I said, for me it is straightforward. I can simply erase it, but for you guys, it's a bit difficult, but please bear with me. Okay? So, now the remaining manipulation, I am going to do it directly. Now, I am not going to ask you whether you have understood it or not. I am simply going to substitute it. Okay. So, now you this I don't have to change anything. This I don't have to change anything. But what about this stuff? What about the remaining two? Okay. What about the remaining two? So this implies, see, my n equal to 0 to infinity. Okay. So obviously, now I am going to bring x to the power n. Okay. So from here, I am going to get n plus 2, n plus 1, a n plus 2. Okay. Now the tricky part. So what you do for these two, you consider these to be the first series and these to be the second series. Okay. So then what is going to happen? We already know what was the formula. K go from 0 to n, right? So if you recall, then K going from 0 to n, it was a k b n minus k. It was something like that, isn't it? Fine. So this is a k. So this is going to be k plus 1, a k plus 1, right? And this is p n minus k. Is it okay with everybody? Right? Similarly for this, once I write, and again, just one thing. This q and this a. Be careful about how you write it. A and q, they should look similar. So this is a k and q n minus k. Is it okay with everybody?
Yes, sir.
Yes, we have already
Yes,
done multiplication of two series. Okay, fine. And of course, n goes from 0 to infinity. So what happens? So now this gives me a recurrence formula. This gives me a recurrence formula. It is given by a n plus 2. So this is equal to minus k equal to 0 to n. Then k plus 1, k plus 1, p n minus k plus a k q n minus k. Sorry. So this is my recurrence formula. Okay, this is my recurrence formula. So now what is happening? And of course, this is for all n equal to 0, 1, 2, 3, etc. That you have to write it down. So that has come from here. Okay. So now if I plug in n equal to 0, so This is going to give me 2a2. Can you tell me what I'm going to get here? N equal to 0. This term. See, basically here it is going to go from k equal to 0 to 0, right? That means I have only one term. I have only one term. So here n is going to be 0, k is also going to be 0. That's it. Is it okay with everybody?
Yes.
Right?
Yes, sir.
Maybe once I move to the second term, it will be more clear to you. Okay. Say this is going to be now both n and k are 0. So this is going to give you, this is going to give you, this is k equal to 0, this is simply 1. This is going to be a1 p0 plus a0 p0. Okay. This is the first thing. Okay. So then what about the second one?
So A naught, Q naught.
A naught?
A naught and Q naught.
Oh, this
A1
is-
is
Yeah. This is Q. I told you to be careful, and I myself has committed the crime now here, right? So here now, if n equal to 1, this is going to give you 3 into 2 a3. So 6a3. This is equal to now 6. Now k goes from 0 to 2. Sorry, 0 to 1. N equal to 1. So remember, n is fixed. N is always going to be 1. Whatever of k, right? So then what is going to happen when k equal to 0? This is going to be a naught, then p1, right? And then this is a naught, then q1, because n is fixed. Okay. So then plus when k equal to 1, this is 2 a2, and then n is already 1, k is 1. So this is p0, and then a1 q0. Have you understood how to go about it? Okay. So similarly, the third term, if you plug in n equal to 2, this is 4 into 3. This is 12 a4. So this is going to be so now n is 2 fixed. N is 2 fixed. So this is going to be 6. Now I start from k equal to 0. So if k equal to 0, this is simply 1 and a1, then p2, then a0, q2, right? Now when k equal to 1, this is going to be 2 a2 p1 plus a1 what? q1. Okay. When now your k equal to 2, this is going to give you 3 a3 p0 and then plus a2 q0. Is it okay with everybody? Have you understood how to manipulate this formula? Fine. Okay. So now, see, I have to prove that. Firstly, the given differential equation has a series solution which is unique. Okay. See, now I have got some recurrence formula. And making use of these recurrence formulas in P, I can get all of them. I can get all of them, isn't it? Fine? I can get all of them. So then what is going to happen? Whatever may be the case. See, I have assumed that y equal to a naught plus a1x plus a2x squared and so on. Fine? So now, obviously, through the recurrence formula, what I will be able to do, here say the recurrence formula, what is happening? In the very first one, like say you have A2 in terms of your A1 and A0, right? And in the second one again A3 in terms of A2, A0 and A1. So that means I will have all the equations. I will have all these equations given by this recurrence formula at my hand, from which I would be able to calculate all the coefficients in terms of some known coefficients, at most A0 and A1. Okay, fine. Is it okay with everybody?
Yes, sir.
Right? So that means I can definitely determine the series. And the series is such that, now if you look at this, y at x not equal to 0, that was my initial condition, right? What happens? I always get it as a naught. I don't know whether I mentioned that. I had already mentioned that. Okay, and then your y prime x naught at 0, that is going to be equal to a1. Is it okay with everybody? Right? So I still haven't proved the uniqueness. I have simply told you that the power series that we have considered, what is happening here? It is satisfying the given initial conditions. So how can you prove that it is unique? Now that solution is unique. Say if you take any other series, like say p and x to the power n. Okay, so then what is going to happen? Like say if you want to plug in the initial condition, you are always going to end up as b naught equal to y at 0 and b1 at y prime at 0. Is it okay? So then those coefficients must be equal. So that means a naught must be equal to b naught and a1 must be equal to b1, right? And since the recurrence formula for the remaining coefficients in the series is going to be the same for both the series for an and bn, you are going to end up with the same solution. Is it okay? Fine?
Yes, sir.
Right? So that proves the uniqueness of the solution. So in tomorrow's class, I am going to prove that the radius of convergence of the series for y is the same as the radius of convergence for px and qx. Okay, I was thinking that I will be able to cover many things, but it takes time. Okay, so then I will meet you in tomorrow's class.